Good afternoon, everyone. Today we're going to start our discussion on machine learning. As I mentioned a while ago, there are three basic types of machine learning. You have supervised machine learning, unsupervised machine learning, and reinforcement machine learning. For the next sessions, we're going to focus on supervised machine learning. It's the easiest of the three because it makes use of structured data. When you say structured data, the uh, the variables are well defined. Okay, so very clear yung data natin. Unlike pag unsupervised, the data can be undefined. No. All right, we're going to make use of two packages. Party, so kindly install this, and Tidyverse, I'm sure you have already installed that. Kindly chat, please, once you have required these two packages. Okay, thank you. All right, thank you. So make sure you have loaded the party package. So let me just, let's first take a look. It's always good practice to take a look at what the party pack, any package for that matter. So it's a laboratory for recursive partitioning. So it's like it's a package which is used not only for classification but for regression, where you classify your objects by doing some process in it. So let me click this. So there are description files, user guides here. Let me go to the description file. Okay, so it's a laboratory for recursive partitioning. So that's where the party comes from, partitioning. Okay, so these are the authors, and it's a toolbox for recursive partitioning. The core of the package is C3, control 3. This is what we're going to use. And then, however, you can make use of some modifications to it. Okay, makikita natin, we'll see later on what the possible modifications are. Okay, so these are the list of the functions that you can make use of. My internet is not that good. Can you still hear me, class?
Yes, sir.
Okay, thank you. Dali lang my internet is so slow. Attendance mamaya na lang. Okay, never mind, class, because it's not working. I think my internet is quite slow now. All right, so now you know the drill, class. You can download, you can access, import the data set. So I have it already here, cardio.csv, and I'm going to run this. I actually have this already. Okay, let me run this. Okay, kindly chat, please, if you have the data shown in your RStudio. Okay, thank you. All right, so what does the data consist of? The data consists of 2,126 observations and 22 variables. So these are the variables. LB, this is the weight in pounds. This is data taken from 2,126 patients in a hospital where they measured AC. These are measures of body metrics, bodily metrics. So I'm sorry I failed to bring the metadata, but this is data about metrics about the heart. So there are others here, okay, but the others are simply mode, mean, median of some other data there, variance, and then here you have here NSP. Okay, NSP stands for normal, suspect, and pathologic. So this is supposed to be a categorical variable. But let's see first how R read this. So let's first, let's create a tabulation of our data. So let's use the table function, table cardio NSP. So we can see here that of the 2,126, 1,655 were classified as normal, 295 patients were classified as suspect of having cardiovascular disease. And number 3 is pathologic, which means there were findings that the person had heart conditions. Okay, so let's take a look at the nature of the data, nature of the variables here. So this is a special table or a data frame. It's a table actually. And you can see here that all the variables are numeric. Including NSP, which is not what we want because NSP is actually a factor. So it's used for categorizing, for classifying our observations. And then here we have the different types, data types, double. Okay, most of them are double, if not all. Okay, so the function summary will give us the different 6 number summaries. And as we learned in the past, this one does not mean anything. No? Kasi yung NSP, it's actually a categorical variable and it doesn't make sense to get the mean, the median, the mode, first quartile, second quartile of a categorical data. All right, so let me go back here. Oh, sorry. So our variable of interest is NSP, which should be a categorical variable, but is now considered as a numeric variable. So easily we can transform this variable into a factor. So let's just create an object, a variable called NSPF factor. Okay, of course you can just change the existing NSP object. But for our purposes, let's just create under cardio a variable NSPF, and then we can convert the cardio NSP into a factor. All right, and then when we run this and try to see class what happened to your NS cardio data set. Tell me what happened. Anyone? What happened to our cardio data set? Comment class? Didn't your cardio data set became 23 variables also? Waiting for your feedback, class. Okay. All right. So you should now have 23 variables, no? Because we added NSPF. And if we check class, let me run the structure once again here. Structure of cardio. Okay. Structure of cardio, you can see that NSP is still numeric, but there's there's a new addition, NSPF, which is a factor with 3 levels. Okay, so that's good. We have converted, or we have generated a new variable, NSPF, which is which is a factor. Okay. Okay. So in machine learning class, we learned before that it's not a good practice to use all your data. If you have 2,126 observations, so to use everything in order to model. Okay, so what do we usually do? What we do is to split your data. Okay, for some, it will split it into two, and they would call it usually training data set and testing data set. So what will happen is that you're going to model your trained data set, and then later on, once you have the model, you're going to use your testing data set to see how your model works. For others, they come up with three splits: training, testing, and validation. In this subject, we're going to just make use of two. Okay, so how do we now partition the data? We can make use of the sample function here. All right, so I give you a minute to copy that, and then mag-set that seed tayo so that we have the same observations. You have the same randomization. Okay, are you done? Kindly chat, please. So we're going to create now a partition data. Okay, and we're going to use the sample function. We're going to split our data into two. Okay, and then our data, which is 2,126 observations, you can just write 2,126, but I prefer using a code for it, n rows, number of rows of our cardio data set. Okay, and then replace is equal to true. What does that mean? Because we're going to draw out, it's just like taking a look at let's say a big bowl, and then you put the numbers 1 up to 2,126 there. And you're going to draw out, let's say, one piece of paper, and that number, let's say, becomes the number that you're chosen is 45, for example. So this 45 will go to one group. Okay, every time you draw, you can decide whether which group, or randomly, the first draw will be for the first group, the second draw will be for the second group. So it makes it more randomized. Okay, and then let's see, after running PD, so let me first erase this. No? Let me delete first the sub objects, and then, so wala na yung si cardio. Let me load cardio again. Sana siya? Hindi ko bigyan makita. Here. Okay. And then let me just layering screen ko because of the sunlight. Okay. Let me convert here. Okay, now I have my cardio with 23 observations. And then let me run this. Okay, what do I now have? I now have this object PD. Okay, and it's used to partition. To see the whole printout, if I type PD, it will give us 2,126 observations. Actually, just 1,000. May limit, no? Okay, may limit sa pag-print. And then these ones are your indices, no? 1, 2, 1, 2, etc. Because I said that split the 2,126 observations into 2. So you have 1, 2, 1, 2, etc. So once we have this, I can now make use of this in order to create my training data set. Okay, if you take a look at this, trained data set is equal to cardio. Okay, so that's our data set itself, this one. And then what I'm going to do is I'm going to subset cardio here. No? Subset cardio into PD is equal to 1, and then row is all the rows, all the columns. So what will be done here is that it will insert all of the ones here into the trained data set. And for the other one, validate data set, let's run this. So you notice I now have okay, I failed to run train. Okay, we have now our training data set and validating data set. Okay, let me just backtrack a bit. Ito class, ito yung distribution. 80% yung pupunta sa first sample, 20% yung pupunta sa next sample. In fact, if you take a look at the distribution, yung cardio natin, ito yung first object, 1718. Si validate, 408. If we check if 2, 2, 1, and row, cardio, multiplied by 80%. Let's see how many was a partition given to 1,700. Okay. So the number of observations times 80%, that's 1,700. Pero dito class, may sobra, no? 1,718. And there's a way to really get exactly. No? But for our purposes, sample to, no? So probabilistic to eh. So hindi natin nakuha yung eksaktong 1,718. But it's important at least na split siya into 1,700. And then of course, the other one will be, so this is n row is the number of rows of cardio minus what will be placed dun sa ay sorry, mali yung spelling ko. All right, for around 425. Okay, kasi 1,007 to, ito 425. Okay, so any questions, class, as far as the partition is concerned? Clear ba, class? You got this? You got this code chunk? So nag-create tayo ng training dataset and we created also a validate dataset. Other calls this testing dataset. Is it clear, class, so far? May I have your feedback? Before I proceed, please. Okay, good. Thank you. All right. Now, my question is, I'd like to first ask this question. Why is it that we have to split your data? Why not just use the 2,126 observations for your model? What do you think is the reason why we split our data? And in the other section, they asked me why 80-20. Is this the standard rule? No, this is just arbitrary. Some would do 60-40, some 70-30, some 80-20. It depends really on the size of your data. Okay, here it's 2,126. Even if you multiply that by 80, we got 17. No? And then for your validation, even if we multiply it only by 20%, so 20% of 2,126, that's around 400 plus. That is sufficient data for validation. Okay, but if you have a smaller data set, example 100 lang, it might not be good to use 80-20 because 80% will undergo the training and 20% will undergo the testing. Kaso konti na lang yung 20%, no? If you only have 100 observations. There are no hard and fast rules about this. There can only be suggestions. Okay, what's important is the model itself. Okay, clear about that, class? You haven't answered the question. Why? Why split our data? Whether it's 80-20, 70-30, what do you think can be a reason why it's imperative, it's important that we split our data? Anyone? Setting a target mean. Okay, so we can test, all right, to avoid. Okay, so the word that we're going to use is overfitting. No? Overfitting. So the purpose is, if you're going to use all the data sets, all the responses, okay, you're going to create a model that seems to specifically fit that data. Okay, and then when you use the data, when you use the model for other data sets, then it might not work, no? Or it might not. It might have a poor predictive capability. Okay, so overfitting should be avoided, okay, because it does not produce really good outputs. Okay, so because what could happen is that instead of modeling the behavior of the data, it can also model some noise. Okay, baka kasama dun sa, it might include the model of the noise itself in your model. Okay, so we're now going to make use of this one. Okay, so let's create an object called 3.1. Okay, 3.1. We're going to make use of the basic function, which I mentioned a while ago, the C3. Okay, so for the party package, this is the sabihin natin, this is the heart and soul of your functions. Okay, and just to indicate where this is coming from, I just wrote here the party package. Okay, and it's similar to a normal ordinary least squares regression. Your NSPF will be regressed on. So let's just use the first three observations. Okay, first three predictors, and then the data that we're going to use is the trained data set. All right, so be clear about this. We're not using data is equal to cardio. We're using data is equal to train. This is the training data set that we mentioned a while ago. Okay, so let's run this. Control Enter. And what happens is that an object called, okay, saan na yun? Okay, bakit hindi nag-fit na yung size ko? Okay. Hold on, class. Okay. Here, we have the cardio data, we have the trained data set, validate data set, and take a look at this 3.1. And 3.1 is not a data frame, it's a large binary tree. So if we click this class, if you view this, it contains several items pertaining to the tree model. Okay, so I leave you guys to try to explore what are included in the tree object that we generated. All right, so let's print this. Let's print whatever can be found in your 3.1. So we can use the plot 3.1 function or the plot 3.1 type is equal to simple. Let's use this first. Okay, kindly chat please if you got this already. If you got the decision tree. Okay, thank you. All right, so let's interpret this. This is our first model where we are predicting whether based on the NSPF variable, if a particular respondent in the trained data set will be predicted as normal or suspect or pathologic. So let's start with this one. The model calls for taking a look at AC first. This is the variable AC. And then it says here that the P is the P value. It says here that is P greater than or equal to 0.001? If it's greater than or equal to, less than or equal to 0.001, then if so, then go here to LB. Take a look at LB. Okay. However, if it's greater than 0.001, you take a look at AC. So you have here a split, right? It's like this is it's like an inverted tree, no? So this is your main root, and these are your branches. On top, if you put this, if you invert this, okay, you'll see that it looks like a tree. Okay, so continuing from AC, you go to LB. if the LB is less than or equal to 136, then you go here to FM. If FM is less than 0.112, then it goes here. So what's this? This is node 4. So these nodes here at the bottom are what we call the terminal nodes. So they are now the container for the prediction. Okay, so this is node 4, node 5, 6, etc. And this one, class, tells us that this path, okay, this path with FM less than 0.112 will yield, okay, take note of this, the probability that the black one here is normal, this is suspected, and this is pathologic. So if you take a look at this path, this means that the prediction for this one is normal. So anybody in the respondent whose AC is less than 0.001, whose LB is less than 136, and whose FM is less than 0.1112, that person will be normal. Okay. If on the other hand, we trace this path and then the FM is greater than 0.112, then that person will be pathologic. Okay, how do I know here, class? Here in the probabilities, 0, 0, and 3. So, 0, 0, and 3. Okay, so this is pathologic, no? And this is node 5, and there are 11 observations that fell under this for the classification. Here, this is 405. So, ganun din, class, the rest, no? So if you take a look at AC, is it less than 0.001? Then go to LB. If LB is greater than 136, then the prediction is that it should be number 2. Number 2 siya. We can see here that the probability of number 2 is greater than that of number 1 and number 3. And so it goes, class. Ito naman, ibang branch siya, no? So all of these branches lead to a particular prediction. Okay? And dito, you can see that most of the predictions fell under 1. Well, that's understandable because 1 has the highest number of observations. This one is number 3. This one is number 2. Okay? A question so far? Any clarifications? Kindly chat, please, if it's clear. Okay, let's see. Okay, good. Excuse me. Okay, so we can create another tree. Okay, if we run this, plot 3.1, that's our model, and type is equal to simple. It will give us the same, however, it's a different presentation of your output. So let's run this. Okay. All right, so take a look at our output here. It's more of a lattice. Okay. It's just the same. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many? Sorry, I think I made the wrong pronouncement a while ago. It's not 19. It's not 19 terminal nodes, class. It's 19 nodes all in all. The terminal nodes here are the ones that are in gray color. Okay, they are the, let's say, quote unquote conclusion nodes. That's where the conclusion lies, based on the given path. Okay, so here we mentioned this a while ago. There are 405 observations that fall under this track. Okay, So you have here the probabilities. Okay, so this is just the same thing. Okay, but personally, I prefer this one because you can already see the probabilities. Okay, in the other one, it's more of a plot, but you cannot see the value of the probability. For this one, the type is equal to simple. You can see the value of the probability. Okay, so let's. Any questions about this class? For you, what's your preference? The simple, type 1 if the not simple, or type 2 if simple? May I have your feedback, class, please? If you were asked to print, what would you print? What will be your preference? The choice 1 will be the first one. Choice 2 will be this one, the simple. Class feedback, please. One. Okay, thank you, Vince. How about the others? One din. Okay. Okay. Ako naman, ang preference ko yung my preference is number 2, yung may box. Kasi naka-define na dyan yung probabilities. For the first one, it's just a plot. So, I don't like not seeing although drawn to scale naman siya, no? All right, so let's now continue. Okay, now the first model that we just use the defaults, no? C3. We did not use minimum criterion. We did not use minimum split. You can, of course, control for your model by using the controls function. And then here, under the controls function, you have C3 control, where you can, okay. What happened here? Iba yata yung naran ko, ah. Okay. Let me just minimize this. Okay, so control for the number of nodes. Okay, this one. So using the same, let's call it 3.1a to distinguish it from the 3.1 a while ago. So you have 3.1a, you have the conditional tree, okay, and SPF, same thing, same model. And then the data is still your training data set. But this time we will be adding here controls is equal to C3 control. We have minimum criterion and then minimum split. Okay, let's find out what this is all about. So go to packages, party. Okay, what's happening? Ayaw pa rin class. All right. Anyway, it defines class what minimum criterion is. This has something to do with the probability and minimum split class. It tells us that before a node can be split into two, there should be at least 50 observations in that node. Okay, so let's just run this and see what happens. So we are the default a while ago for the minimum criterion. The default here class is minimum criterion is 0.95. Okay, let me just double check. Because I'm having a problem with my okay. Not working. Okay. Mahina siguro internet ko. All right, so let me go here. I'll leave you guys to explore other types of refinement for your decision tree. The first one was just bare. Bare lang yung ano nga, yung decision tree natin, ano. Ito class, and then I plot this. So what do we notice here? So hard to see here, class, kung ilan yung terminal nodes, no? Let me print this using simple. Okay, there are now here 12 terminal nodes. So kanina kasi 11 lang. And then there are 28 nodes all in all. Kanina 19 lang, di ba? So there are more nodes here. Okay, let me just okay, so you can see here, class, that mas maraming terminal nodes ngayon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A while ago, I think there were only 9 ba? So you can modify your your decision tree by changing the parameters. That's just what I wanted to point out. But of course, there has to be a caveat for this one. Generally, the more terminal nodes, the better, as compared to just a few terminal nodes. Okay? So, however, pag masyadong marami, if there are so many terminal nodes, then this can also affect the accuracy of your model. Okay, so let's go here. Okay, so let's have another example. And here we're calling it 3.1b. Okay, I'll give you a few minutes to run that code, to copy that code, and then we'll discuss. Okay, are you done, class? Now take note here, same model din to, no? NSPF, LB plus AC plus FM, train data set still, and we're adding controls here. A minimum criterion is 0.999, and then minimum split is equal to 500. Okay, and I'll point out what this minimum split is all about and how it can be very constricting with your model. So here I'm writing minimum split is equal to 500, and let's see what happens here. I run this, and then I just, let me just print this. Okay, so what happened to our model? Take note now that there are just 4 terminal nodes. And if you have only very few terminal nodes, this will really affect the accuracy of your model. Let's try to see, class, this one. So this one predicts that all of this path will be predicted as normal, because this is the probability of normal here. On the other hand, this path will be predicted as suspect. This is S. Okay, 0.40, 0.49, and 0.10. The second here, which is suspect, has the highest probability. And this one, 0.79, 0.14, and 0.06, this one is also normal, and this one is definitely normal. So notice that you have 4 nodes here, and none of this predicts pathologic. So that means, class, the 100 plus pathologic will be already in error, right? Because here you're not able to predict even the pathologic. So you'll most probably you'll generate bigger error terms. Okay. So you can play around with this. By the way, what do you notice about the mean split? What do you notice about the mean split is equal to 500? The mean split, class, tells us that before this particular node will split, there has to be present more than 500 observations. So if you take a look at this came from this one, this came from this one, right? So that's around 720. So this can still split because here there are 720 observations. So when you split this, 416 and 314, this can no longer be split. This can no longer be split, class. You know why? Because this is 416. It's less than 500. Okay, and the minimum split should be 500. This same thing also for this one. Okay, for this one it's 800. So this can be still split, but perhaps it did not split it anymore because the answer will still be P. Okay. All right, and we have to contend also with the 0.9999. All right, if I change this, for example, into 50, suppose I make this 50. Let's see what happens, class, to our model. So which means, class, that if the minimum split is 50, this may still split. This may still split. Okay. Or let's make it 100 this time. 100 for your minimum split. All right, let me run this. And let me run this simple. Okay, now the terminal nodes increased, became now 5, right? It became now 5. And here, this one, 405 and 11, this came from node number 3, that's 500, 405, so it can still be split. This one, 314 here, and this is 400 plus. So this one can still be split, but notice it was no longer split. This one can still be split, but no longer split. This one can still be split, but no longer split. And you know the reason why it no longer split, because of the p-value, okay? The condition of the p. All right, had we changed this into, let's see, if we make this 0.9, minimum split at 100, let's see if it will change the model a bit. Okay, so you can experiment with the different different methods. So you notice here that by reducing the minimum criterion, it generally increases the number of terminal nodes. Okay, compared to the 0.9999 mean split of 100, that one only had 5 terminal nodes. This one has many more. If I change this and make this 95, run this, and then run this. Okay, it has less, no? It has less terminal nodes. Less than 0.999 because the 0.9999 has only how much was that cost? Sorry, I forgot 9999. Okay, much less. No? All right, so you can experiment with this class. What's important is what was the original here, class? 3.1a. Okay, let's increase this 500. And then let's rerun our 1B. Okay, only 4. Okay, well, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. I think 11. No? Okay, so let's compare between these two models. Now, first we will have to predict. We'll make use of the predict function here, predict, and then we're going to use the 3.1a, and the data is trained. Okay, so what are we doing here? We are asking R to generate the prediction of the trained data set using the model 3.1a. And what's 3.1a? This is our 3.1a class. No? Ito yun, yung 0.9 at saka 50. Yung 3.1b natin, 0.999 at saka 500. All right, so if we run this class, and then run, let's make it train 30 by 20. So what does this mean? It will give us the value of, wait. I think I'm missing something here. Okay. Side by side lang natin. Okay, let's compare the first 20 values of the prediction and the actual data. All right, so this is the this is the prediction class, no? 1, 1, 1, 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The first 9 observations is normal. But if you take a look at the trained data set, natin itong train NSPF. I just want to make use of the all right. So compare natin to class, no? Ito yung P1T is a predicted value, no? 1, 1, 1, 1, 1, etc. Ito yung actual value, yung train NSPF. 2, 1, 1, 1, 3, 3, 3, 3, 3. So you can see for the first 10 observations, marami ng ano, no? Marami ng misclassified, no? Right? Marami ng misclassified. Ito yung predicted value natin, ito yung actual value. Okay? So let's summarize, class. Summarize natin yung ano yung predict natin tapos i-compare natin siya sa I'll share this with you. Para mas mabilis. Okay. So what are we doing here? I'm creating a table. So you see here the function table. So ano yung nasa x-axis? Yung nasa x-axis natin is the predicted value. Ito yung function niya. Predict ng 3.1a. And yung nasa y-axis will be actual data coming from your trained data set, and then yung NSPF. Okay, so you're going to create a side-by-side a table predicted versus yung actual para makita natin kung ilan yung tamang predictions versus the wrong predictions. All right, so I'll run that. Dapat sinama ko to print. Okay. What do we have here? Predict niya na normal when actually normal siya. So this is a correct prediction. Predict niya na normal yung individual pero turns out that it's suspect. So wrong prediction to. Predict niya na normal, it turns out that the person is already pathologic. So dito sa prediction 1, only 1304 is correct, 131 is wrong, 109 is wrong. Same thing here with prediction number 2. Yung model natin, predict siya na normal, 95 yung tama, 44 mali, 24 mali. And also last thing, predict niya as pathologic 11, when in fact, pathologic siya. So walang mali o tamang dito, no? Okay. Yung diagonal siya ang tama, di ba? Sorry ito. Itong 1, 3, 0, 4, 95, at 11. This is a prediction ng number 3. Okay. Lahat ng predict niya tama. Wala siyang mali na predict niya na number 3 pero number 1 pala yun. Alright, so let's now count. Ano ba yung ano? Before that, let's now, di ba may ano tayo, model 3.1b. Let's now use that here to create another table, but this time, i-compare natin yung second model natin versus yung actual. Okay, so I gave this to you. Okay, if you run this, run everything, yan magiging result class. So comparing yung 3.1a natin at 3.1b natin, you can see that 3.1a outperformed si 3.1b. So depende yun dun sa control natin, no? So yung minimum split natin, so you can still experiment on that and try to see if you can come up with a better model. So process pa rin ng experimentation yan. Unfortunately, hindi pa kaya ng party package to give a best approach kung ilang split, kung ilan yung other parameters. All right. So this time, class, yung ginawa natin dito, this is just for the testing data set. Okay, this is for the test data set. This one, I'm sorry, trained data set. So this time, let's see how our model will work if it's if we're doing the validation data set. Okay, this is what we were saying a while ago, that let's not load all the data, all the observations in your model, because we will be suffering from overfitting. So now let's test. I'm going to just use the same thing. Did I give you this? Not yet. This code, class. Okay, in the interest of time. All right, so this one, we're creating a predicted one for the validation, P1V. Same code, class, using the same model 3.1a, but this time using the validate function. Okay, so I'll just run this. Okay. If we type is equal to probability, it will instead give us not the not 1 or 2, but rather the values, the probabilities class. Okay, so let me just, okay, I'll delete this just to show you, and then just do the head. Head P1V. Head, oops. Head P1V. Then let's just get the first, maybe 15 observations. Okay, so I'll run this. I'll run this also where type is equal to probabilities. Ano difference between, sorry, I should have used, let me just retype this using P. This one class will give us the predictions, this one P1V, as the number itself, as a factor itself. On the other hand, this one, type is equal to probability. This will give us the predictions. Okay, so what happened here? Sorry, this should be P. If I just go here, class, P1 P. Okay, take a look at this. These are probabilities class. No? Probability. And the value of this is 1. Kasi mas mataas nga yung probability of observation number 1, 0.98%. And it's consistent with the P1B here. Okay, it's almost time, class. Allow me to finish this, class. If you need to go, you may go, please. And before I continue this, I'll just share the remaining part here. Okay, kindly copy this to your, I'll split it into 2 because a while ago it did not fit. Kindly copy this to your R file, and then I hope you can run it on your own first so that the next time we meet, okay, the next time we meet, we will just discuss this. So I already shared with you the remaining code chunk. Okay, this is using another package. It's called the R-part package, this one. Okay, decision tree with R-part. All right, but let me just finish this, class. So where are we here? All right. Okay, so let's now predict 3.1a, and then, so this is actual. This is actual. So now, class, here, tab.1a VIP. This is for validated data. And let's run this. So for the validated data class, all right, we're having a, for using the 3.1a class, we're having a accuracy rate of around 80%, 20%. So this is for the validation data set. Now, a while ago, by the way, did I discuss this? I don't think so. Here, this is for the what's that? Sorry, trained data set, no? And we're comparing the performance of the model 3.1a and 3.1b. So for 3.1a, we had 82% accuracy. For 3.1b, we only had 80% accuracy. So it's quite a big difference, no? 2%, that's quite a big difference, especially if you have a big data set, 2,000 data sets. So that's a big difference. It turns out that your 3.1a performs well class, performs better compared to 3.1b. Now, if we use the validate data set class, so this is a data set that has not yet been seen by R. You notice that the result for 3.1a is 80%. So not bad, not bad. It's not too far away from the actual testing data set. Okay. All right. So that ends class our discussion for this one. Okay. The remaining part of this is using the R part. So I hope you can run this on your own. Okay. It's almost the same thing. Iba nga lang yung you have a different way to print your decision tree here. Okay. So please run this on your own. Try to see what's how pareho lang naman class yung ano, 'di ba? Yung confusion matrix natin dito. It's just the same. So that next meeting we will focus now on the random forest. Okay. So this is just an example of how decision trees work as far as classifying, using this as a regression for classifying for factor variables. Okay. All right. So with that class, I stop recording.